Okay, so for the second talk of this morning's session, we have a walk through hyper-Kähler geometry, Emanuele Macri from Paris.
All right. So I hope this thing works. So great. So well, let me start by saying that okay, I've been here. I've been in Seattle 20 years ago and Salt Lake City 10 years ago. It's such an honor for me to present this talk. It's the first thing. And second thing, I'm the last speaker of the morning, I guess. So I would like to really thank by heart the organizer for putting this conference through, which was excellent, and especially given the time. So thank you very much. But I think from all of us. All right, so let's start. So yeah, so I was deciding what to talk about, and well, there has been a lot of progress in the past 10 years on hyper-Kähler geometry. Here I'm talking about hyper-Kähler manifolds in the compact sense. So there is a beautiful theory about hyper-Kähler varieties in the quasi-projective case, but here during this talk I will only talk about projective. Okay, so that's the first thing. And then deciding what to talk about, there is many things going on. So I choose a few of them in this talk, and I'll try to present them as a walk through various subjects. So here is my plan. Sorry for the picture. So I will start by saying something. So I will start by defining what a hyper-Kähler manifold is, and then we'll walk through several properties of hyper-Kähler manifolds. In particular, I want to study their geometry by looking at the Lagrangian fibration structure. We'll see there are some fantastic development that I'll mention also later. And then I'll go to hyper-Kähler manifold. They always have something to do with moduli of sheaves, so stable sheaves. Again, recently there's been a huge development. We saw also something not related to hyper-Kähler, but still motivated by this in the talk by Eyal yesterday, and in the talk by Kieran especially. So we'll go a bit through it. And then at the end, I'm doing category theory at the end in a certain sense. So I will say a bit how the part about categories will connect to these three dots. Okay, so that's the plan. And so let's start. So I'll start with the definition. So I'll work in the smooth case for the moment. So what is an hyper-Kähler manifold for us, for this talk? So I'm looking at varieties over the complex numbers. And so for us in this talk, everything is projective. There is a beautiful counterpart in the analytic setting. We won't talk about this so much in the talk, but it's important to keep in mind that. So hyper-Kähler manifold, so which I will always denote by HK, is the following. So a smooth projective variety with the following property. So there is a non-degenerate 2 form, which I call it sigma, which so this is symplectic manifold in some sense. And then I want this to be the smallest possible. So smallest possible means I want that the symplectic form is unique up to constants. And I want that topologically is the smallest possible. It means that the variety is simply connected. Here, when I mention something about topology, and especially when I mention about cohomology of group cohomologies, I will mention always M with Euclidean topology. Okay, so I will. And so let me make a small motivation while these are somehow there are several motivations why we are interested in. There is a metric motivation, so more from the differential geometry point of view. We won't talk about this so much, but we'll try to motivate more from the viewpoint of rational geometry. So this is mostly motivation for the week before. So one of the fundamental theorem about varieties with first-Chern class equal to 0 is the Boville-Bogomolov decomposition theorem. So this is based on some result in differential geometry, actually, essentially by Berger classification of holomorphic groups. And so what does it say? Let me state it again in the smooth setting. So if I have a variety which is smooth and projective, again, I take the tangent bundle and I compute the first Chern class of it, and I assume that this is 0 in cohomology. Okay. Then the statement, sort of surprising, says the following: say that up to a finite étal cover, which I call it X prime, this thing splits. Okay, so if I want to classify varieties with these properties, I only need to classify each of these factors in the splitting. So there are 3 types. So the first one is an abelian variety. So that's his first piece. The second are what sometimes are called the strict Calabi-Yau manifolds. I won't talk so much about them, but I will need to use the letter CY a bit later in the talk. So that's why that's what will stand for. And the third type of manifolds that we have are hyper-Kähler. Okay, so that is where we're aiming at. So we're aiming classification of variety with these properties, and that's somehow we just classify one piece of it. And so what it means to classify, but we need to know two things. First of all, we need to construct them, and this turned out to be a very difficult problem actually. And we want to classify in the sense that we want to know up to deformations. For example, if I fix dimension, if there are only finitely many deformation type. Okay, so that's a bit some questions, some general questions that we want to answer. So for the motivation from rational geometry, actually, this is not quite enough. So the interesting thing is that there is a singular version of the theory which works as well as possible. And nowadays, actually, the definition is better and better. I think 10 years ago was still not understood so well the concept of what a singular symplectic variety was. And nowadays, there's been incredible advances on that. And so now we have a definition, if you want, on what something which should be reducible symplectic, which is very similar actually to what the definition I gave here. Essentially, it's the same definition. The only difference is that I'm asking for some nice singularities, let's say terminal to factorial, and I'm asking the symplectic form to be defined on the regular locus. And that's essentially the definition. And similar for the second condition, I would like that the varieties will be simply connected when I look at the regular points. So, and the interesting thing is that there is a theorem which is exactly the same as the theorem over here. So the theorem says that if I have some variety with some nice singularities, such that the canonical bundle is numerically trivial, then the same decomposition holds up to both finite in codimension 1, let's say. So this is called a quasi-étal morphism. And so again, I will have the composition in three pieces. One is an abelian variety. One is also called the irreducible Calabi-Yau variety, which is some definition. I'll give this next one. And the next one is what is an hyper-Kähler variety. Okay. And so this is more interesting because if I want to classify varieties with codaric dimension 0, that's what I end up with. Okay. So this theorem is due to many people actually. Let me mention briefly by name. So I think Drouel, Greb, Genancia, Quebecus, Peternel, Öring, and also in the whole theory, there is always an analytic version, as I said, even in the singular case. And this has been settled in a paper by Becker, Genancia, Christian Lenny. Okay, so that's a bit where the theory stands. Okay, so we want to classify these varieties. They help us to classify varieties with codaric dimension 0. And so here we are. All right, let me give you some examples about them. So in dimension 1, in dimension 2, sorry, let me say one thing. So since there is a symplectic form, elementary linear algebra is telling us that the dimension of the variety is even. Okay, and I always denote it by 2n. So for n equal to 1, it's pretty simple. Whatever definition we have, these are so-called K3 surfaces. And fundamental theorem by Kodaira from the 60s says that, well, there is not so much thing to do. They are all deformation equivalent. Okay, so let me also mention that hyper-Kähler manifolds or variety as well, they have a beautiful theory they behave very well from the viewpoint of deformation theory. So this means that the local deformation is actually smooth, so you can freely deform as you like somehow without any problem. This is known for K3s. This holds true also for hyper-Kähler. And so examples, as I said, there are not so many examples. There are actually essentially 4 types of examples. There are 2 families, which are the families discovered by Beauville. And so this gives example in each dimension. So there are 2 types actually. So the first one is also called the K3n types. And I'll discuss an example in 1 second. So these are all deformation equivalent to Hilbert scheme of points on a K3 surface. And the second class of examples is very similar. Just instead of starting with a K3, I start with an abelian surface. And then in a beautiful paper, somehow, in a beautiful 2 papers, somehow O'Grady found two exceptional examples, which we'll discuss a bit later, which are one in dimension 10, again coming from a K3 surface, and one in dimension 6, again coming from a similar construction for abelian surfaces. I will not define them now. I'll talk about them quite a bit later. So let me give an example. The easiest example is the symmetric square. So this is the example in blue. So I start with a K3 surface, and then I look at a set of 2 points on such a K3. So what is the idea? So I want to construct an example which has the definition we saw before in dimension 4. So what I do, I start with a K3 surface, and I take the product. Okay. So this is fantastic symplectic manifold. It is simply connected, but it has two symplectic forms. And so what can I do? Well, it's very simple. I take an involution, switching the factors, and this symplectic form, if I choose it nicely, will pass the quotient. But now the quotient is singular. And so what can I do? I just, for some miracle, the singularity are not so bad. So singularity are just cones, so quadric cones times the diagonal in some sense. And so how do I resolve them? I just take the cylinder. And the nice thing about this thing is that it's T star of P1, which is one example of symplectic manifold. And so you can imagine that by gluing the symplectic form, I get something which is the Hilbert square. So this actually on the diagonal does remember the scheme structure of the 2 points. And this is an example of hyper-Kähler. Okay, if you want to have a proof, you just complete the diagram on the upper left corner, and you do a calculation. It's not so hard actually to finish the computation and to prove that everything works. Okay, this is an example to do Fujiki. Actually, it was before Beauville, but I think it was unpublished for a bit. Okay, great. And the example in dimension n, they're very similar. Same construction. Just you can do the same construction in codimension bigger than 2. And then in some sense, for all this computation, we don't care about the part in which is too singular somehow. All right, so these are the examples. Are there any questions so far? So far, so good? Great. So let's start with the first piece. So I want to talk about, so what is a hyper-Kähler in some sense? Hyper-Kähler is a dynamical system in mathematical physics. And so what I'm looking in an analytical system, I'm looking as so-called integral systems, which are the one which have a lot of integral of motion. Okay, in the algebraic geometry language, it is a Lagrangian fibration. So before defining them and say what are the main conjecture, let me say a few motivations. So there are two motivations for studying hyper-Kähler with this Lagrangian fibration structure. And one thing is the following, is that this helps to construct examples actually. So I think this was an idea due to Eyal Markman, and then developed in various papers by Donagi Markman, I think Markushevich as well. So you start with what? Well, if a Lagrangian fibration by Arnold-Liouville theorem, we'll see in a second, is essentially an abelian variety over an open subset. And so what you try to do is try to find some special conditions such that this thing extends to something projective with some global rigid geometry. So that's one motivation. And the second motivation is a paper that appeared last week, actually. And I think Phil will talk about it this afternoon, I think at 1:30. And so what is the idea? The idea is that if you have there is a conjecture about hyper-Kähler, if this conjecture holds, so this means that every hyper-Kähler could be deformed to something which admits a Lagrangian fibration, then the analog of Kodaira's theorem that we saw for K3 surfaces holds. So this means that, well, there is not a unique family, but fixing dimension, there will be only finitely many deformation families of hyper-Kähler. Okay, so this theorem is very nice because actually it does hold even in the singular case. So this is really something which is analog to Kodaira's theorem somehow, and somehow we are still far away to understand how many types we have, but still this will help us. And there are some conjectural bound also on other things, but anyway, so this is a result by Engel, Filippazzi, Grier, Mauri, and Svaldi, and I think, as I said, Phil will talk in this afternoon. So let's start with this one. So what is the main conjecture about hyper-Kähler and Lagrangian structure? So this is the so-called SYZ conjecture. So this is for people coming from Brownian geometry, it is just the abundance conjecture, a version for hyper-Kähler. So it's very simple. I start with an hyper-Kähler manifold. The singular case will work as well. I take an F line bundle on M, and the question is it semi-ample? Okay. And by base point free theorem, it's not so hard to see that there's only one case to worry about, which is the case where the line bundle is not big. Okay. Or said in topological way, if I take the C1, I pair it 2 n times, take the integral, I want this guy to be 0. And the 1L to be not trivial, otherwise it's easy to understand. Now, hyper-Kähler manifold, if you've never seen before, they're super rigid geometry. And so this theorem might look surprising, but actually it's not so hard to prove it once you understand a bit the structure of hyper-Kähler manifolds. So we say the following. So assume the conjecture. Assume I have an F-line bundle which is not big, so we satisfy this case here, and which is semi-ample. Then I look at the induced morphism, and the induced morphism is actually a Lagrangian fibration. So there is no morphism. If I look at morphisms with connected fibers from a hyper-Kähler manifold, which are not birational and non-trivial, this must be a Lagrangian fibration. Okay, so this is sort of surprising, but as I said, the proof is not so hard actually. And what does it mean a Lagrangian fibration? It means a morphism from M into B. B might be singular, and that's a problem. There are conjectures also on what B is, such that if I take the general fiber and I take the symplectic form is trivial on the general fiber, and of dimension, which is half the dimension of the variety. Okay, so it's really a Lagrangian submanifold. And by, as I said before, by Arnold-Liouville theorem, this will be an abelian variety. Okay, so any morphism from an hyper-Kähler manifold is a Lagrangian fibration, essentially. Okay, so that's the part which is interesting. And so two little remarks. So first of all, this conjecture is true on all examples that we know. Okay, and we'll see a bit about this later. So for example, the 4 example we know, this conjecture holds. And second, as I was remarking before, is the second Betti number of our manifold is greater or equal than 5 by elementary lattice theoretical results. If the conjecture holds, then I can always deform the manifold to something which admits a Lagrangian fibration. And so this is exactly the setting in which the theorem that was mentioned before will hold. Okay. And so the idea here is that hyper-Kähler manifolds are not as complicated as Calabi-Yau because in some sense they are relative abelian varieties. Okay, there's nothing so incredibly far from being an abelian variety, but they're special one. So I need some condition to compactify them. All right, so let me give you 2 examples of this structure. Okay, so the first one is a classical example by Beauville and Mukai. So I'll tell you first the geometric part, and then we'll see later the Mukai interpretation of this system. So I start with a surface, actually, any surface. How do I create a Jacobian for an abelian variety fibration? Well, it's very simple. I take a linear system, I take smooth curves, and over each smooth curve, I take the Jacobian. Okay, this will give me a Jacobian fibration over a linear system, which is some projective space. Some opening in a projective space. And so why do we need K3 surface? So K3 surface help us in the following thing. First of all, it helps us that the curve has genus G, okay? And the linear system has also genus G. So we are in good shape somehow. So this is the right dimension, at least, for having a Lagrangian fibration. And the symplectic structure on S induces by some way that I will talk a bit about this later, induces actually symplectic structure on this whole space. Okay, and so the statement here is that in the singular case, you can compactify this thing. So you can compactify and obtain a variety, a manifold actually in this case, which is the formation equivalent to a Hilbert scheme on a K3 surface, maybe another one, together with a Lagrangian fibration, which extends this Jacobian fibration. Okay, so this is a standard system. This is a standard example of an hyper-Kähler with a Lagrangian fibration. Next, there is some variation of it, but it's not so far away in some sense. So now I start with some geometric condition, and this construction will always go like this. So now I start with a cubic in P5, so a cubic hypersurface, which is smooth. So this is a fourfold. I take the hyperplane section, and then I look at the following thing. I look at the same idea. So I take a hyperplane section, and I look at all smooth hyperplane sections. So these are smooth cubic threefolds. Okay, and the linear system is a P5. And so the interesting thing here is that to a cubic threefold, well, there is no Jacobian, but there is a natural analog of the Jacobian of a curve, which is the intermediate Jacobian. So this is a classic construction due to Griffiths and studied in many cases related to the rationality of the cubics. We saw something in Stefan's talk as well. And so what is the point of this is that this intermediate Jacobian is also something of dimension 5. It's a principal polarized abelian variety of dimension 5. And so I can do the same thing. I can look at the relative intermediate Jacobian over the smooth locus. And now it's some standard argument, which maybe I won't discuss too much in detail, but it's not so hard actually, that this fibration actually does have a symplectic form. And again, the same theorem as the previous one works. Although this is much harder actually, and this is a recent, well, fairly recent result by Radu Laza, Julia Sakai, and Claire Voisin. It says that in this case, I can compactify still. And this is actually an example of an hyper-Kähler manifold, so smooth, of a Grady type, of a G10 type, okay? Together with a Lagrangian fibration, which extends this fibration in intermediate Jacobian, okay? So these two examples are some construction. This is exactly what I was telling you before. You have some special abelian varieties, and you want to compactify somehow, okay? And so the surprising thing is that this seems very hard. It seems that, well, okay, it's actually, boy, the random abelian variety, family of abelian varieties won't compactify nicely. So, well, okay, these are nice examples, but seems like that's it. But recently, actually, it has been understood that actually, if I allow that the compactification might be slightly singular, then it's actually not so hard to do that. And so here's the theorem that I think Julia was supposed to speak on Monday, maybe about this. So, but let me try to present her theorem. And so, as I said, it's very hard to construct example, right? So, sorry, so this is slightly technical from before, but actually the theorem is not so technical. It's just technical to write, but not to explain actually. So how does it go? So let's assume that I have. Let me first read the theorem and then I explain it. So let me assume that I have some base B, which is fairly general. The only thing we need is that it's normal. Okay. And let me take an open subset inside the base, and let's assume that I have a manifold. I can allow singularity also to this one, but for simplicity, let me state it in the smooth case. So I have a smooth quasi-projective symplectic variety. So symplectic means there is a symplectic form here. Okay. So that's the first thing. This is fundamental. So I have a variety which is smooth quasi-projective. And let's suppose that I have a fibration, but I don't ask anything about this fibration except to be surjective with connected fibers, but not necessarily proper. Okay, so this will be important for later. So this is just a fibration from a quasi-projective variety into an open subset of a normal projective variety. And now the point is the following. So let's assume that there is a smaller maybe subset for which the fibration is actually a proper Lagrangian fibration. Okay, so I have two subsets. I have a larger one and I have a slightly smaller one in which the fibration is actually proper. Okay, so the fiber is actually a proper subvariety, which again by Arnold-Ville is an abelian variety. Okay. And let's assume two conditions. Let's assume that the original open subset is large. So large means has codimension greater or equal than 2. Okay. And the second condition, okay, this seems fishy, but actually in all examples, this condition is sort of automatic because the way that we construct a symplectic form is by some cycle condition, and this condition actually in this sense becomes automatically satisfied. Which means that I compactified my mu anyway, I take a resolution of it, and then the only condition I want is that a symplectic form will extend to some 2 form, maybe with zeros, I don't care. The only thing is that I want it not to have poles there. Okay, so it extends as a regular holomorphic 2 form. And then the theorem say like, boom, then it's it. Then I can compactify. And the compactification will be symplectic. Okay, and will be projective. Okay, and we'll have, okay, then you can run an MP, it will have some nice singularities, let's say terminal equifactorial, and the Lagrangian fibration will extend as well. Okay, so that's the theorem. It seems surprising, but let me see in practice how does it work. Oh no, sorry, let me mention another theorem, which is also very recent. So there is an evolution of this theorem, which is due to Yuchen Liu, Ziyu Liu, and Chenyang Xu. They say that if I add a slightly more stronger assumption on the variety mu or on the fibers, so for example, one assumption you can ask is that, so I know that the fiber will be an abelian variety. Let's assume that this abelian variety is simple, for example. And let's say that the fibration is not isotrivial, to avoid the trivial example, then M actually will be a reducible symplectic. So it will be one of the factors which in theory appears in the decomposition theorem. Okay, so this is sort of so this means that I need to control these two conditions. And so let me make an example of that. So let's go back to the previous two examples that we saw. So the smooth locus is our open subset U prime. So that is nice, is a nice projective fibration, beautiful. But that's not enough for this theorem, because the smooth locus inside the linear system will have complement of codimension 1. Okay, so that won't work. But no problem. So the only thing I need to do, I need to extend it slightly in codimension 1, not necessarily in a proper way. And so if I take a curve, for example, with a node, then I'm good to go. I just take the Jacobian there. The only thing I have to make sure is that I have a symplectic form. If I do that, then it works. And indeed, this works in the two previous examples. And indeed, this theorem was motivated by the LSV paper, where indeed they just do that. So once you extend to the nodal locus, not necessarily in the proper way, but in a symplectic way, then you win. Okay, so that's the content of this theorem. So that's pretty strong, and that will provide a lot of examples, actually. The only thing that we lose is that a priori the example, we have no control on the singularities. And so, sure. In the Zariski, that's correct. Thanks, Eyal. Yes, it's correct. So Eyal comments was that I'm using Euclidean geometry, Euclidean topology in general, for when I speak about cohomology, but in this sense, it's really Zariski condition. Okay, so it's a codimension 2 Zariski condition. Thanks. Sure.
So the example on the previous page
Sure.
of the multiplied family of intermediate Jacobians, does that compactification to a smooth hyper-Kähler have a modular interpretation?
We'll go to that. Thanks. That's a fantastic question. And this is the second section of the talk. Actually, it's not so trivial, actually, but it is. The only thing is that you have to define what sheaves, somehow sheaves on hyper-Kähler are horrible. But we'll see that there is a notion which is due to Eyal. We'll see in a second. There's a notion due to Eyal and Beckman, which essentially single out some special sheaves which behave like in the surface case. So the two examples actually are similar. Just the first one is easier because that's a moduli space on a K3. The second is harder because it will be a moduli space on an hyper-Kähler. Okay, but that's a fantastic question, and we'll go to that. Yeah. Other questions or remarks so far? Okay, great. I'm late, but okay. Good. So let's do two more examples. And so the first one was this recent paper by the same author as before, so LLX, Yuchen, Ziyu, and Chen Yang, that says the following. So this is a generalization of the LSV examples. So I'll give you the construction, but it's the same idea. So I start with a cubic fourfold, and there is some recipe, which I'll describe in a second, how to produce something which is projective, but unfortunately singular. But this variety is very special somehow. There will be some new example. In some sense, there are some O'Grady type example, but singular. Okay, so the B2, here's the condition here is that B2 is greater or equal than 24. For those of you who have seen Kieran's talk, this is really, that shows that it's a new example somehow. And also comes with a Lagrangian vibration, and there is some weird condition that the base actually, in this case, it's actually singular. So these happen also already in the fourfold case when I have something singular, but this is some interesting weighted projective space. And so when you have some geometric construction, then you can generally produce something interesting. The second case to study is the case of Gushel-Mukai. And so that's what we did with Kira and Julia, which is the next theorem, essentially with the same method. And so this will appear hopefully. So let me say briefly what it is. So this is much more similar to LSV in some sense. So it's easier, but on the other hand, it's more complicated because cubics are easier to deal with. Gushel-Mukai is slightly harder because they refer with Grassmannian. So what is a Gushel-Mukai sixfold? It's very simple. It's a variety with a 2-to-1 cover of the Grassmannian 2-5, where this cover is ramified along a quadric. Okay, so that's what a Gushel-Mukai is, sixfold. And then again, same example, same technique, slightly more complicated or easier from one hand to the other, produce for you another example. And so the idea is that this example actually will produce a lot of examples, hopefully, of O'Grady type, all with the same conditions. And what is the idea? The idea is that the second example actually might be something general. So in this case, well, let me do one slide, and I'll comment about how this can be generalized. So the idea is the following. The idea is always to produce some interesting variety out of that. So if I start with a cubic fourfold, so the idea is to use a construction by Iliev and Manivelle and to look at cubic fivefolds containing the fourfold. And then I do the same thing as LSV. I look at the intermediate Jacobian, and I'm good to go. Okay. There is some slightly complication because cubic fivefold are a bit too many. There is some isomorphism, and so they need some non-trivial GIT part to get rid of this ambiguity somehow. For us, it's slightly easier because it's very similar to the case of LSV. So I'm just taking hyperplanes. But again, there is a small symmetry because the involution on the sixfold will give a non-trivial map on the hyperplane section. So I need to do something else as well. Anyway, so this is a construction, and somehow the key point is to find some more somehow. And sorry, yeah, there is a question here that somehow, well, okay, to be really wanted something non-trivial, I would like also that the regular locus to be simply connected. This is not known yet. I'm not claiming it's harder or easy, just that we haven't done it yet. All right, so the idea what it is, the idea is try to do the same thing, but so a nice example on which to try with is in some sense these examples are related to Lagrangian subvarieties of some hyper-Kähler manifold. I will explain in a bit in a bit about this thing. And so the idea is to find some interesting Lagrangian subvariety, maybe some manifold. This is very hard to do that, but there is some example where we can study is when you have an involution, maybe it's an anti-symplectic involution. And so this will be like a generalization of the second theorem, which maybe will produce examples in all dimensions. Anyway, I will comment a bit about this later, or I might discuss about this. All right, great. So that's the theorem. Let me say one more example about this SYZ conjecture. So the point is that, okay, let's prove it at least in one example. And that is very hard, as you can imagine. And so we did prove with Olivier Debar, Daniel Heubergs, and Claire Voisin, at least in one example. And so the example is the case of fourfolds. So what is the idea here? The idea is that, well, okay, I want to prove that there is something semi-ample. So what is the easiest possible situation in which I can add some assumption is that if there exists an abelian fibration, in this case an abelian surface fibration, I will want, for example, to have a principal polarization coming along the fibers. And so this numerical condition, which seems a bit bizarre here, exactly say that. So this is like I expect to have a fourfold with a principally polarized abelian surface fibration. And then under this condition, actually, we were able to prove the conjecture. Okay, so in this case, actually, the conjecture hold. But again, there is a small issue with this thing, is that, okay, it holds, then I have a Lagrangian fibration of the structure, but then, okay, then I can use it to say something about the manifold. And actually, what we get as a corollary is that actually is not a new example, this thing. Once I have this condition and I have a fourfold, then it's one of the things we know, actually. So as a corollary, it's true that we proved the SYZ conjecture but then somehow we use this actually to prove that actually the variety that we get is actually located in two type. So this is interesting from the viewpoint of classification because we are using the abelian fibration structure to deduce some geometric property, and but in this case we just classify. So we say that there is nothing else. Okay, it was actually the same type as what we know before. All right, so good. So are there any questions for the first part? So this is the part about geometry. And now let's try to answer Jim's question. So I'm just taking the same theorems and I want to reinterpret them in terms of sheaves. Okay, this is classical in the hyper-Kähler setting, as you saw probably in Kieran's talk yesterday. And so let's go to the next step, which is moduli sheaves. And so let me give also here a bit motivation. So why do we care about moduli? Or why do we care about sheaves? Well, I guess the main issue is that we want to use sheaves and Chern classes to represent certain Hodge classes, for example. So we saw, for example, something in Alstock yesterday But this was also due to Mukai at the beginning when he talked about some cases on the Hodge techniques. The second thing that moduli space are useful for is that you can reduce to some problem something in lower dimension, of course, and then you have a method to control singularities. So for example, the theorem we saw before, we have a compactification, this is great, but we don't know if it's smooth or singular. So the moduli space techniques allows you maybe to give an answer to that. And for example, when Kieran discovered his two new examples, somehow indeed he used the moduli space structure to understand how the singularity look like. And then actually, well, ample cone, we have a result with Arend a few years ago. So you can use moduli space to understand ample cones. And then finally, even to prove the theorem that the Lagrangian vibration exists, the moduli structure is helpful actually. And this is a result by Eyal in the case, for example, of K3n type, or Yoshioka in the case of Kummer type. Okay, so let's go. Let me first do a very quick crash course on moduli spaces. Actually, it's not a crash course, but it's fine. So let's take a projective variety and let's fix an ample line bundle on it. And let's fix some numerical class. For the moment, I'm very vague. I will be more precise later. But for example, in general, you fix the Hilbert polynomial. For us, X will be smooth. And so for us, V will be like Chern character, or even better, the Mukai vector. We're going to see in a second. And so I denote by MXHV the moduli space of equivalence classes of semi-stable sheaves on X with a fixed numerical class. Okay. And so the key property here is the following. It is a projective variety, so it's already compact, and the singularities I was saying can be studied. Okay, so for example, we know that the tangent space is the X1, and by using some Kuranishi theory, you also know that there is an explicit local description of the moduli space nearby. Okay, so this depends on X2. This is useful in several contexts. I will come back to this a bit later with a more precise statement about that. Okay, so anyway, so these are the two ingredients that are useful for us. And so by these two ingredients, it's super somehow, for example, to go back to the compactification, so let's go back to the Mukai system, I can reinterpret it as a globally, as a moduli space of rank 1 torsion sheaves of fixed degree, let's say, on support on curves. And now the global geometry of the moduli space in this case is just governed by the local geometry, sorry, is related by the X1, but X1 is easy to compute by Serre duality. Okay, and so it's easy to see that the compactification I get is smooth, at least for the very general. Great. So now the next slides will be a bit technical, so we'll go quickly. It's not important so far to know this part, but I just put it just for completeness. So for a K3 surface, all moduli theory is controlled by the so-called Mukai-Hodge structure. Okay, so this was in the original paper by Mukai, beautiful paper from 1987. And so how do I look at the sheaf theory? Well, I take the H2. As we know by global Torelli, H2 controls all the geometry of the K3 surface. To see moduli spaces, I just look at the whole cohomology. Actually, this is the wrong way to think about this. Somehow the way to think about this is to introduce the Mukai pairing, which is a version of Poincaré duality, actually. And then the part in H0 and H4 is actually a copy of an hyperbolic lattice. And so the right way to think about it, I'm taking the H2 and I'm adding a copy of the hyperbolic lattice. So this is fundamental. Keep in mind, we're going to go get something about this in a few seconds. So there is a Hodge structure. It's not super important. And this is a numerical class that I fix for K3 surface just by some Riemann-Roch computation. It's generally useful to look at the Chern character modified by the totals. That's our numerical invariance. Now, fundamental theorem, I'll be very quick about this. So this is due to many people. It's Mukai, Beauville, Kuleshov, Hoybrex, O'Grady, Yoshioka for the smooth version, and then Perigora-Pagnetta for the singular one, and O'Grady for the case of OG type. It says that if I fix a Mukai vector, if I let the polarization to be generic, then I have a numerical precise criterion in terms of Mukai pairing to say whether the moduli space is non-empty, which simply says that if it has the expected dimension to be non-zero, then it's non-empty. It's an infinite leaf. And second, this gives you example of irreducible symplectic varieties with nice singularities, which are smooth of K3n type if the vector is primitive. Okay. and with one exception in the non-primitive case, which is OG10 type. But the issue there is that the moduli space is singular, and so the only space that of which you have a modular interpretation is the singular O'Grady space. And then by studying singularities, you get some smooth variety, which is exactly the type of OG10 that we know. And second thing, okay, this is not super important for now, you also can describe the cohomology of the moduli space. So this is, the H2 was you can write it easily, and this was, essentially comes from a result of Beauville on Hilbert schemes, but actually you can describe the whole cohomology. And this we saw in Julian talk, which is due to Eyal Markman. So you can describe actually the whole cohomology by using moduli space structure. Okay, great. So let me go back to the local structure. Even in the, okay, smooth in general, easy, but even in the singular case, the moduli space is cut out by quadrics. So what does it mean? So I look at the tangent space, which was the X1, and then the point is that I have my Kuranishi map, which is not important what it is, which goes into the X2. And so the moduli space locally will look like the inverse of this moment map modulo some group of automorphisms. So for K3 surfaces, this Kuranishi map is super simple. It's just quadratic. So it's just given by the Yoneda product on the X1. So X1 goes into X2. So it's simple. It's very easy to study singularity because I know explicitly how it looks like. And so we would like something like this in higher dimension. That's we'll be very happy about it. The issue is that, and we saw already in some previous talks in the afternoon, when you go to higher dimension, of course, it's horrible. Moduli space are horrible, and that's the end. But recently, there was some progress. The interesting thing is that okay, the moduli space are horrible in higher dimension, except that maybe if you fix some interesting Chern character, then they become manageable. So that's a bit the idea. And in Eyal's talk, we saw this very nicely from the viewpoint of abelian varieties, for example. So these were called the K-secant, but somehow the analog that Eyal also introduced in the case of hyper-Kähler is what's so-called atomic sheaves. So this is just a condition on the Chern character. So if I fix this condition on the Chern character, somehow by some mystery, the moduli space becomes much nicer. And so here is the atomic sheaves. So let me first make an analogy. What time is it? Ooh, okay, I'm good. I'll do quickly. So the analogy is the following theorem by Voisin, which is fundamental theorem for studying Lagrangian varieties. So he's saying the following thing. He says that I take an hyper-Kähler manifold, I take a smooth Lagrangian manifold. How can I deform them? And so what she proves that somehow you can deform as much as you want. But what does it mean as much as you want? Well, I just look at the restriction map between the cohomology of the manifold and the cohomology of the Lagrangian manifold, and I look at the image. So I can deform as much as possible if and only if the class stays of Hodge type. So that's the deformation. If and only if the morphism of restriction has rank 1. So as one-dimensional image. We know as a one-dimensional image because if you take an ample polarization, we'll go into an ample polarization. But that's it, okay? And so the notion of atomic is very much similar to this theorem. The only thing is that I want to include also non-commutative deformation of my M. And so this is a bit bizarre. What does it mean in this context? It means that, I have the canonical bundle. I would like the canonical bundle to be in the image of the restriction map. Okay, so this is a special Lagrangian inside this thing. And so here is the definition. So this is due to Beckman and Markman. So I take an hyper-Kähler manifold. I say that the sheaf, take a sheaf. I say that the sheaf is atomic if the same condition. This is slightly technical. I'm sorry about this. So I have the obstruction map to deform the Mukai vector, and I want this to be with image of dimension 1. And the second condition, I'm sorry, this I'll go quickly anyway, this is very technical. I say this is one obstructed if it has, if the actual obstruction, which is something which maybe I won't talk about, has also one dimension. So atomic is not really the nice name for this thing. So should we call the cohomologically minimally obstructed maybe? So atomic was used by Beckman, but there is nothing atomic in it. Just some so, but it's a nice name actually. So, but there is no. So it's easy to give a talk with by using this name. And so, but let me explain what does it mean, this definition, which seems incomprehensible. So the H2 and the HH, they control the formations, including non-commutative one. So if you see I put the composition of the H2, so the H1 of the tangent, we all notice control complex deformations, like in Claire's result before. And so if I look at H2M or M, this controls some sort of Jerby deformation. And if I look at the symplectic, the Poisson form, which is on the right-hand side, this is something which you can imagine as a Poisson structure. So this gives you something which is non-commutative. Okay, so I want to look at all the formations. And so let me say the key important part, that being atomic is only a condition on the Mukai vector. There is no algebraically. It's just a purely topological condition. It's just asking that the Mukai vector stays of Hodge type along the deformation, along the maximum it can. And the second condition says that it actually deforms. Okay, so these are the two deformations. In the case of Lagrangians, they coincide. This was one theorem. In general, we don't know. Okay, so, but anyway, the important thing here is that it's just a condition about the Mukai vector. And so key properties is the following. So if it's one obstructed, then it's atomic, and conjecturally also converse holds, at least if you have simple sheaves. Okay, so this is a result by Eyal and Beckman. Second, we saw the Mukai structure before. There is an analog one for hyper-Kähler. So same as before, but not all objects have a Mukai vector in this way. So it's a standard Mukai vector, but it has if the definition before it holds. Anyway, so this is some technical condition. Wall crossing, we know that if you vary polarization, this is horrible in higher dimension, not for these sheaves. And this is out by O'Grady. They say that they behave like surfaces. They're wall and chamber structure. They are beautiful. You can study them as much as possible. For condition, they deform as much as they can, and locally the moduli space is cut out by quadrics. So the Kuranishi map is again very easy to study, but very easy, easier. Okay, and so this is the result by Eyal, Beckman, Verbitsky, and Meazzini Onorati. Okay, final thing, final. There is symplectic form. This we know, and in the one obstructed locus, this symplectic form is unique. So unique means that the construction that we have produce the same form. Okay, so that's the best we can for having something which should be hyper-Kähler. And the last condition is important for the end. It's a derived invariant. So I can just use Fourier Mukai techniques, and they will send me atomic sheaves in atomic sheaves. And this is a result by Tellman, and then improved by Beckman and Markman. Okay, examples. There are not so many examples, but if I have something in Lagrangian, we saw already what it means to be atomic. It means the canonical must be in the restriction map. And then with Alessio Bottini, we have slide generalization, which classifies essentially all of possible atomic sheaves on Lagrangian. And other examples are actually rigid, which is the example by Kiran that we saw yesterday. And these are useful for understanding, for example, Torelli type questions. There is a classification of them, but they are rigid, so this means the moduli space are just point. But it's interesting because it's a smooth point. So that's the nice part about the result. So they're really one obstructed, they actually are smooth. There is some other example due to Eyal about semi-rigid things. And so the main thing here is the following, is to answer Jim's question. So we saw the construction of LSV, now let's give a modular interpretation. But modular, this means that really I want a smooth O'Grady example to be a modular space. And so we use atomic sheaves now. So let's go back. So we have a cubic fourfold, we have an M-pole. And so what is the hyper-Kähler associated to a cubic fourfold? This is a Bouville-Donaghy variety. So this I just look at the Hilbert scheme of lines inside the cubic fourfold. And so by Bouville-Donaghy, this is an hyper-Kähler fourfold of K32 type. And so the theorem by Bottini says that the construction we saw before can be reinterpreted as a moduli space of atomic twisted vector bundles on the final variety of lines. Okay, so that answers your questions. And so now we are good to go, because now we have an interpretation of the smooth moduli space, of the smooth O'Grady example as a moduli space. And so we can apply, for example, techniques like due to Eyal, for example, to study its cohomology and so on and so forth. And the idea, okay, let me do very quickly, and this is an idea that it works in general, that was I was saying before. So I look at the final variety of lines, and I look at the surfaces. And in this case, it's very easy to find which surfaces I want to look at. I look at cubic threefolds, and I look at lines in the cubic fourfold, which are contained in the cubic threefold. And then I look at rank 1. It's like the Beauville example, as I told you. The only thing is that atomic sheaves behave nicely when they have vector bundles, not when they have torsion. There is still a bit of a theory to be developed. And so you need Fourier-Mukai transform techniques, which in this context are much harder. But fortunately, as we saw also in Julian's talk, there is a fantastic result by Arinkin that allows to do these computations. Okay, and so that's exactly what Alessio uses in his theorem. And the expectation, as I was trying to say before, I think I'm close to be, okay, it's fine. I must finish it. The expectation is that you should find some interesting Lagrangian. And even the two singular examples that we saw before is still not known yet, but there is a result by Gu and Ziu Liu that say that actually, well, at least birationally, they are birational to a moduli space of atomic sheaves as well. Okay. And so again, so the interesting thing is that I take, for example, some hyper-Kähler variety. As I said, that one way to get a new example, I take an hyper-Kähler manifold with an involution. I look at the fixed locus. This is rigid in general, with symplectic involution, with anti-symplectic involution. The fixed locus is a Lagrangian submanifold, which is rigid. But maybe if I look some multiple of it, this thing will move, and then I can look at atomic sheaves supported on them. And then maybe this will produce an example which will, in any dimension, of generalized O'Grady type, like generalizing to these two examples that we saw before. So the example of Gushel-Mukai is exactly step 0. So the surfaces that we look there are just 2 times the class of the fixed locus. Okay, anyway, so we need example of Lagrangian. Let me finish quickly. So this is a very hard problem, of course. We simplify into something which is very hard as well, which is finding the interesting Lagrangian submanifold inside hyper-Kähler. Now, category theory can help a bit, because again, we are reduced to something of lower dimension, right? So category theory helps for Fourier-Mukai techniques. These, as I told you, these are needed in the whole theory, so we need to look at categories. To understand non-commutative deformation, this is a question about categories. But the interesting thing is that you can also look at something about Lagrangian submanifold by using categories. So I'm really quickly out of time, so let me put the whole slides all together, and I will be quick anyway. So the prototype example, this is just the second to last slide. The prototype example of a non-commutative whatever category is the Kuznetsov component for cubics again. So last time we see cubics, so I take a cubic fourfold, I look at the derived category, and inside there is some special derived category which is called the Kuznetsov component, or the residual component, as Kuznetsov called it. And so this is I'm just taking all complexes which are orthogonal, which have no cohomology, and no cohomology when tensor by -h, and no cohomology when tensor by -2h. And the interesting thing is that this is a Calabi-Yau 2 category, which means that it looks like a Calabi-Yau 2 manifold, which means it looks like a K3 surface or an abelian surface. In this case, it's just a K3 surface. And actually, it's actually non-commutative deformation in general of a K3 surface together with a polarization. So polarization is harder to say here what it means, but polarization means an ample line bundle. But for us, an ample line bundle induces a notion of stability, and so the polarization means a notion of stability. Okay, which in this context is what is called a bridge stability condition, which was mentioned by Roman in his talk. And so I do the same thing. I look at cubic threefold, there is a Kuznetsov component, and then I look at the push forward, and this gives me like some sort of non-commutative curve inside my K3, and I should think about a non-commutative curve in some sense. And so the interesting thing is that the interesting Lagrangians that we have come from moduli space on this non-commutative curve. And so the idea will be like, okay, maybe there is a simplification. So I start now with a category, with a K3 category, and I try to find the non-commutative curves. Maybe it's easier, maybe not, depends. But the issue is that you will need to develop the theory for this. And so we are not so far away, but still a bit yes. So let me maybe quickly mention the results and I leave the question open. So if you have something of K3n type, the first thing you have to do is that you have to realize as a moduli space over something. A priori, just a deformation of it. So there is a construction of my Markman and Merotra that say that you cannot do in general, when it's very general at least. And there is a recent work that we have with Chuni Li, Alex Perry, Paolo Stellari, and Xiaolei Zhao that says that actually you can actually construct this kind of polarization as well. So at least the first step we are there. And if you saw Laura's talk in the second day, she talked about the case of Kummer type, where actually you have stronger results. Okay, I'm sorry, I just rushed the last part. I think I'm done. So thank you very much.